department, and this is a joint work with Professor Gulotty. So he works on IPE and political methodology. So in this paper, we'll talk about how to use instrumental variable to learn the ATEs of always takers and never takers. So IV estimation has been widely used in empirical political science studies to address selection problem in observational data. So if we allow flexible heterogeneous treatment effect, then IV only identifies late, which is an average treatment effect for complier group, for compliers. So an implication of the heterogeneity assumption is that late doesn't equal to ATE, and also late doesn't equal to the ATEs of always takers and never takers. And so we believe that in the study of persuasion, researchers are interested in the ATEs of always takers and never takers. So in empirical study of persuasion, researchers are interested in the following parameter. So what is the effect of some information treatment on people's action of interest? So there will be two examples in this context. So first, in authoritarian government, the authoritarian authorities will use propaganda to persuade their people to believe in their performance. And in democratic societies, the democratic candidates will use campaign to persuade their voters to vote for them. And people may respond differently to this information treatment. For always takers, they may be the most responsive people to the treatment because of their high prior of the support of the state of the world. And for never takers, they may be the least responsive people to the treatment because they are low prior on the state of the world. Okay, so in this project, we will do four things. So to facilitate our extrapolation, so we first rephrase the IV model in Imbens and Anger's paper into the latent utility approach. And after that, we will provide a set of identification results, point and partial identification results on the ATEs of always takers and never takers. And we will provide simulation studies. However, I will not go through the simulation due to the time constraint. And finally, I will talk about applying our methods in Kern and Hainmueller 2009 political analysis paper and do some extrapolation exercises. So first, so these are the four assumptions that you will encounter in any causal inference class when you are learning IV. So to use an IV to learn to do causal inference, we need four assumptions: IV exogeneity, IV relevance, exclusion restriction. In addition, we also need monotonicity assumption. However, after Imbens and Angrist published this paper, there are so many critiques on the paper. So especially from Jim Heckman. So the first critique is that the monotonicity assumption is actually pretty ambiguous. To be precise, the IV monotonicity actually doesn't equal to the mathematical monotonicity. To illustrate my point, I will use this example. Okay, so consider we have an instrument where it takes three values, 0, 1, and 2. The mathematical monotonicity may imply one of this relation of potential treatment status. D0 smaller than D1 and smaller than D2. Of course, the order can also be reversed. That's mathematical monotonicity. But the IV monotonicity actually says for any Z and Z prime in the support of Z, either DZ smaller or equals than DZ prime or vice versa, almost surely. So this ordering actually fits the IV monotonicity assumption. So D0 smaller than D1 and D0 smaller than D2 and D2 smaller than D1. But this ordering is definitely not that D is weakly increasing or decreasing in Z. So to conclude, so actually mathematical monotonicity implies IV monotonicity, but not the vice versa. And second criticism on the monotonicity assumption is that you don't have substantive interpretation of this assumption. So to be precise, what I mean is that there is no natural connection between the IV monotonicity and the rational choice theory. So conceptually speaking, what IV does in this context is that IV is shifting people's decisions of taking the treatment. However, you're restricting this, you're imposing this uniformity assumption in the sense that IV only shifts people's tendencies of taking treatment in y direction. That is, you either increase people's tendency of taking the treatment or decrease. So conceptually speaking, this is a little bit strange because in Imbens and Engrist framework, they allow very flexible heterogeneity in the treatment effect. But in the first stage, they are restricting how flexible IV can shift people's decisions into selecting the treatment. Actually, there is asymmetric relationship within this framework. So to provide a solution to these two critiques, Wittloso in 2002, he has a paper that tries to link the IV model to the selection equation in traditional literature. So now let's rephrase everything into the selection model. So it turns out that the monotonicity assumption, it can be reformulated as this selection equation. So this U is the latent utility that is all observable to the researchers, and the Z is the instrument, and V is some function that we need to estimate. But the intuition of this selection equation is that you are using instrument Z to shift people's valuation of taking the treatment. And people are having this utility threshold to compare the valuation of the selecting into the treatment versus not selecting into the treatment and making decision whether or not they select into the treatment. So by doing this, we have very nice interpretation of the first stage regression based on the rational choice theory. And because of this framework, this rephrasing monotonicity into this selection equation, the independence assumption, IV independence assumption, can be reformulated as instrument independent of the joint distribution of potential outcomes and the latent utility. So to repeat, as analysts, we don't observe latent utilities, okay? And then for IV relevance, it's very, we only need the function Vz to be a non-trivial function of Z. That is, we can't allow Vz to equal to a constant. That's the pretty simple assumption. And then the exclusion restriction remains the same. And we also need a more technical assumption. That is, we need the latent utility to be continuously distributed. And it turns out that you can show these 5 conditions are exactly equivalent to the IV assumption in the Imbens and Engrist IV model. Okay, so because if we have this latent utility, we can now introduce this whole new treatment effect parameter called marginal treatment effect. So before we talk about this MTE, i.e. marginal treatment effect, let's do some normalization. So remember that we're assuming U to be continuously distributed. And this implies that we can renormalize the distribution of U to be a uniform distribution. And another implication of this normalization is that we can interpret VZ as propensity score. So when this event, when U, this random variable equals to little u, which is a realization of the U equals to VZ, when this event happens, this exactly describes the set of individuals who are at the margin of selecting into a treatment. Okay, because of this, we can define the marginal treatment effect as the average treatment effect for the individuals who are at the margin of selecting into the treatment. So this MTE framework is actually very, very powerful because many treatment effect parameters, say ATE, ATT, ATU, late, selection on the gains, can be rewritten as weighted average of MTEs. And these weights are identifiable. And so after we set up the framework, we can now talk about our extrapolation exercise. So remember that we're interested in these 2 target parameters, that is the ATE for always takers and never takers. And we also know that the distribution of Y1 for always takers is identifiable, and the distribution of Y0 is identifiable for the never takers. But we still want to learn something about the ATEs for always takers and never takers, okay? And remember, we also have this MTE framework. We will try to rewrite everything, these 2 target parameters, into weighted average of ATEs, weighted average of MTE function. It turns out we can. It's summarized in this theorem. So this theorem says that the ATE for always takers and never takers are just some weighted average of MTE function, and the weights are just some propensity scores. P0 is a probability of D equals to 1 when Z equals to 0, and P1 is the probability of D equals to 1 when Z equals to 1. So after we have this theorem, a natural question to ask will be, can we put strong enough assumption to help us point identify these two parameters? It turns out that we can. The intuition of this assumption that we impose is that, what if we impose parametric assumptions on this MPE function? That is, we either assume it's linear or parametric, and if the instrument creates enough variation on the treatment taking decision, we can point identify this function. And because we can point identify this function, we can point identify these two target parameters. Of course, because we know MPE and all these classic target parameters, say ATE, ATT, selection on the gains, we can identify. And this proposition summarizes the intuition that I just talked about. But of course, there are definitely criticisms on this proposition. So a natural criticism will be, why do we even believe in these strong parametric assumptions on a marginal treatment effect function? So people may not believe. And also, if you think about this assumption conceptually, it's actually very strange, because the motivation of MTE is that we want to allow very flexible heterogeneity of the treatment effect with respect to the unobserved latent utility. But when you are putting this parametric assumption, you're actually restricting the flexibility of such treatment effect heterogeneity. So to respond to this critiques, our approach, we ask ourselves, can we do partial identification? In terms of partial identification, what I mean is, can we identify a bound for the ATEs of always takers and never takers? It turns out that we can. And our strategy is to rephrase this extrapolation problem into a linear programming, or we can also call it linear optimization problem. Okay, so I'm gonna talk about the intuition about this linear program right now. So first, we need to remind ourselves that we observe estimates like OLS, late, and also these 4 sample moments where indicator function D equal to D, Z equal to Z times Y. These are the 4 sample moments that we observe from the data. And the nice thing about these estimates are that they are also weighted average of MTE function, and their weights are identifiable from the data. Remember, so these estimates, they're weighted average of MTE, and their weights are identifiable. And we also show that the ATE of always takers and never takers are weighted average of MTE. And these weights for always takers and never takers are some propensity scores, right? It's also, we can compute from the data. But what we don't know is the potential functional form of the MTE function. And these estimates, say OLS, IV, and these sample moments, they actually provide some information on the possible parametric space that the MTE function can take, right? And this same MTE function lie in this parametric space generates the ATEs of always takers and never taker. And an implication is that only a set of values for the ATEs of always takers and never takers will be consistent with the parametric space of the MTE function. And the parametric space of MTE function is given by this OLS, late, and sample moments. In other words, we can partially identify the ATEs of always takers and never takers. And of course, if our information is strong enough, the bound for the ATE of always takers and never takers can shrink to a scalar. And in that sense, we can still actually point identify these 2 target parameters. And this intuition is just summarized in this proposition. And so far, we have talked about rephrasing IV model into the latent utility framework and introduced the concept called marginal treatment effect. And we also show that ATEs of always takers and never takers are weighted average of MTE function. And we show that the parametric assumptions on MTE function guarantees point identification. But sometimes, if we don't believe in the parametric assumptions on the MTE function, we can do partial identification by doing this linear program. Okay, so now let's go to the empirical application. So we're looking at this Kern and Hainmueller 2009 Plateau analysis paper. In their paper, they're looking at the effect of watching Western Germans TV on Eastern Germans' support for communism. So they get the data, they get the survey data to do this research, and survey data the survey was conducted between 1988 to 1989, which is very close to the collapse of Soviet Union, actually. And of course, the identification challenge in this effect is that people are self-selecting into watching Western German TV or not, right? So to solve this selection problem, they use a binary instrument which measures whether people live in Dresden district or not. And this Dresden district is very far away from Western Europe. And because of its due to the topological reasons, people living in this district, they can't receive, it's very hard for them actually to receive the TV signal from Western German. And our conjecture in this context is that this self-selection may suggest that people may have some private knowledge on the potential treatment effect. And people are acting on this potential treatment effect to self-select whether or not you take the treatment or not, given the instrument, okay? So to remind ourselves, our target parameters are ATEs of always takers and never takers. So we first do point identification. So first we replicate the paper. So this is our replication. It's very close to the original results in the paper. In these regressions, we don't control for anything. The IV are super strong, by the way. And the results shows there is a positive effect of watching Western Germans TV on the support of communism for complier group. In other words, watching Western Germans TV actually increases compliers' support for communism. To me, I think this is a very striking result. So now let's do some extrapolation, okay? So first, let's do point identification result. So again, we're parameterizing, where we're imposing linearity assumption on the MTE function, and we're getting those two extrapolated results. So the results shows that the effect of Western Germans TV is positive for always takers, and the effect of Western Germans TV on support of communism is negative for never takers. Although many people may disagree with us on these results because of the poor parametric assumption. But the more interesting results are from the bounds by linear program. So for the ATEs of always takers, the bounds are always pretty wide, but we think even we control the H cohort in our linear program. But I think this is driven by the small sample problem because there are only 2% of the people are always takers, which means there are like 30-something people in the sample are always takers. But the results for never takers, the bounds becomes very tight and narrow when after we control the H cohort in our linear program. So the results shows that there is a negative effect of watching Western Germans TV on the support of communism for never takers. And our interpretation is that these never takers, given their high prior support of communism, they are acting as if they have private knowledge that they anticipate such negative effect of Western Germans TV. Thus, they self-select to not watch Western Germans TV. Okay, so to conclude, in this paper, we're trying to do some extrapolations on the ATEs of always takers and never takers using instrumental variable. So we first rephrase everything into the latent utility framework and define marginal treatment effect. And we also show that ATEs of always takers and never takers are weighted average of MTE functions. And we show that as long as we put enough parametric assumptions on this MTE function, the point identification is possible. But if we don't want to invoke this point parametric assumption, we can also do linear programming, which is to rephrase everything into an optimization problem. And in the paper, we actually compare our linear programming approach, this partial identification approach, with many existing competing partial identification strategies. And it turns out our linear program approach performs better. In terms of better, what I mean is you can construct narrower bounds with less assumptions, less additional assumptions on your data. Okay, and we also apply the methodology into this Kern and Hainmueller paper the interesting result shows that there is a negative effect of watching Western Germans TV on people's never-takers' support for communism. And our interpretation is that these never-takers, they're acting as if they are anticipating this negative effect of Western Germans TV. Thus, they self-select to not watch the Western Germans TV, given their high prior support of communism. And I think that's, and the final takeaway point is about whether or not this paper actually connects with machine learning. I talked with Bobby before. I think this paper is remotely related to machine learning because this is about optimization. And in Becker-Friedman Institute at U Chicago, we have a conference called Optimization Conscious Econometrics, and we invite all the people from stats studying machine learning and optimization to talk about how optimization theory revolutionized the machine learning. So I think our paper actually still remotely relates to machine learning. Yeah, that's all of our presentation. Thank you. Yeah. Yeah. Yeah.
Sorry about that. I was double muted. Yeah, optimization is, thank you very much. That was excellent. Yeah, optimization is, what I was saying before was optimization is extremely important in machine learning. In fact, I took a class at Berkeley that was on only optimization. It was really fascinating, great class. And it was being taught by someone who was doing, was at Facebook AI research. So, you know, the knowledge of optimization and optimization problems is just, especially when it comes to these really complicated models like deep learning models where you have to, you know, they take a long time to train and they're extremely complex, and yeah, optimization is super important. So this is a great application of kind of optimization method. So anyway, I have a question, but I'm gonna kind of ask folks who are out there and other places if they'd like to ask a question to the presenter before I ask my question.
Arthur, you don't have to share your screen anymore. You can shut that off.
Yeah, you can just shut your share screen off.
Yeah, I think Zenobia has a question. Yeah.
Oh, Zenobia. Hey, sorry. Okay.
Oh, okay. I thought yeah.
Anyone?
So, yeah. One question I had, because I shared Jason's concern that you're not supposed to do this, in the sense that I mean this in a good way, in the sense that identifying behavior and always never takers simply can't be done from the data.
Yeah.
In an IV.
Yes.
Right. So it literally, so like crazy things could be happening over there. And then you're using parametric assumptions to put bounds on those crazy things that are happening.
Actually, we're not. Our response is that we're not putting parametric assumptions, because it turns out this new latent utility framework is exactly equivalent to the IV model in Imbens and Angrist. So in that sense, in that linear programming extrapolation approach, it's completely assumption-free. Yeah.
Wait, it's assumption-free in what sense?
There's no additional assumptions.
There is no additional assumptions.
But you need a linearity assumption or something like that.
In terms of identification results,
yes.
In terms of formulating this linear program, we don't need any additional assumption, because all these treatment effect parameters, they are weighted average of some conditional expectation. So it forms a linear space. And conceptually, you can do linear programming. But to make the linear programming feasible, to make this feasible, we need to put some parametric assumption on the MTE function.
Yeah.
But that's why we loop so many parametric polynomial orders on the MTE functions in our linear programming application. However, the bounds are actually not very sensitive to the polynomial order for never takers. Yeah, I think it's very robust. Yeah.
So one place to push on this in terms of presenting.
Yeah.
Or in terms of the presentation, because the idea, at least in my head right now, is making sense. Yeah. It depends on that sort of linear extrapolation, right? And extrapolation problems are difficult because anything could be happening over there conceivably, right? So any information you're bringing in is by assumption.
Yes.
That said, some assumptions are better than others. So is there some way to build faith in your model in the observable data. So rather than check off 25 different models with different specifications and show you sort of get the same result, is there some way using the observed data or using some held out data or something like that to say, you know what, this data performs better for the compliers or something like that? And I have some faith it will extrapolate on outwards.
So now we haven't think about this because
or what would a bad model look like
in our simulation?
In your setting.
Yeah. In our setting, say for example, we have a proposition that if we put parametric assumption on the MT function, very strong, we say it's linear, and then we can point and identify everything with binary instrument, right? And in our simulation, we actually show if the MTE function is approximately linear, and then your extrapolated results will be very close. However, if the MTE function, the true MTE function, is not very linear, and the extrapolated results will be very far away, and that's where things can become very bad. But again, the linear programming approach is that since we're only approximating a unknown function within interval 0 to 1, actually in optimization theory, the Bernstein polynomial, if you use this Bernstein polynomial to approximate this, approximation will be very, very good. That's why it's actually very robust. Yeah, that's our response. Yeah.
Okay, so what's helping constrain the problem is you're only estimating a bounded function.
Yes.
So you could use some sort of, you said the Bernstein polynomials or any sort of Fourier decomposition or something that just is any bounded basis function should perform well.
Yes.
Okay.
Furthermore, the bounds are constrained by the values of the observed parameters that are themselves weighted functions of the MT function. So it's actually using the fact that all of these regular observed things that are locally identified, like the late, like the IV estimate, like the OLS estimate, themselves put bounds on that space. So
how does it put bounds on the space?
Because it's assuming that the MTE functions that we're trying to put constraints on have to hit certain values. In particular, we know the weighted values that they have to hit for those observed quantities.
For example, OLS and limit. Yes.
So it's not just a linear extrapolation. It's using the theoretical construct that there's this latent utility out there, and that's driving people's decisions to opt in or out of treatment.
So you can constrain the space of possible functions by enforcing that it
hits
give you the
values.
lake back and gives you the least squares estimates back.
Yeah, and the conditional moments, the cross moment. There's some cross partials that we have to hit. So there's like 5 or 6 things that all have to happen all at once. And so then the additional question is actually not to really constrain the functions. It's more about a computational feasibility problem.
Yep. So then you do have to be assuming that the marginal the MTE function doesn't change by compliance status, right?
No. The MTE function it's the function for across all the individuals. Yes.
Okay.
Yeah.
So it has to be smooth though.
It has to be smooth.
Yeah.
But so what's precluding it from being just really crazy for nevertakers and you not knowing that?
Then
it wouldn't. Which part of it?
I'm sorry. I'm. You need to be assuming that there's some similar function running from the compliers that are observed to the always takers and never takers, or at least some similar function class or some space of functions, right?
Some space of functions, yes.
Okay, and then you're limiting the space of functions on the observed data and assuming that carries through to the always takers, never takers.
Yes, because the same selection equation drives the decisions for every people in the data, complier, always taker and never taker. That's the intuition. Yes.
Okay.
That's why this approach is actually choice theoretic based.
Yes.
Yes.
And I like the Heckman. How do you say the name? Vitalisil.
Vitalisil.
Vitalisil. I like that better than the Angrist Imbens approach. It just takes a lot more to get there.
Yeah, Vitalisil is a Heckman student, by the way.
Is it? Okay.
Yeah, he's at Yale right now. Yes.
Because their works on that has been interesting. Okay, cool. I think I almost buy it, but I'll send you an email after I look at the paper more closely.
Yeah. Thank you. We appreciate that. Yeah.
All right.
Yeah.
Any other questions?
Can I add a quick suggestion?
Yeah.
So you mentioned in your presentation that the exclusion restriction assumptions still have to be met when we use your method to estimate the MTE. And I was just thinking, when you talk about your example in Dresden, is exclusion restriction really met here? Like, because when you explained the nevertakers, it seems like they by choice don't choose not to watch the West German TV. And I was thinking, then is it possible that people choose to live in Dresden to begin with because of their existing pre-existing belief? If that's the case, then it doesn't seem to me that so it's not exactly related to your project, but I feel like the exclusion restriction assumption here is a little bit shaky.
So can I respond?
Yes.
Okay. So actually in Kern and Hainmueller paper, they justify this. Before the collapse of Soviet Union, the labor market is very, very ill-functioned. So spatial sorting is actually impossible. That's how so people you actually can't move freely in Eastern Germany. Of course, I'm not an expert on Eastern German, but that's what their papers say when they are trying to justify the exclusion restriction. Yeah. Does that answer your question or no?
Yes, I will write you an email later.
Yeah. Thank you. Yeah. Thank you.
All right. So I just had a question that was a little bit more general, and that is, the kind of conceptual idea of estimating the treatment effects for always and never takers.
Yeah.
So one thing that I don't, and perhaps you can help me out with is is there like a subset of problems in which this estimate in which the very idea of estimating treatment effects for always or never takers breaks down? Because I was just kind of trying to think through different types of examples where you would have situations where you have compliers, always takers, never takers, but in one situation, let's say like a vaccine or something, because that's what's on everyone's mind, right? It's clear that there's effects, there's treatment, there's like if the vaccination is the treatment and the disease probability of disease or whatever it might be is the outcome.
Yeah.
Then it's clear that there would be effects for always and never takers because of the compliers, right? Like in other words, the compliers taking, let's assume like there's a contained population. There's a lot of assumptions I'm building in there. There's like a contained population and everyone is randomly assigned a vaccine, something like that, right?
Yeah.
So then the compliers would have effects on the always and never takers in terms of their probability of disease. But let me just finish. But like, so that's one context where I think that makes a lot of sense. But then, like, if you take, like, let's say the treatment is a heart, pressure medication. I'm getting very practical, like a little bit away from political science. Like, what would that mean conceptually to estimate the effect on blood pressure of always and never takers, since the compliers don't have any kind of, or they shouldn't have any influence on those two other groups? I don't know if that makes complete sense, but I'm just trying to work through, it's a very interesting paper and it kind of introduces an idea that is conceptually very interesting and a little bit hard for me to wrap my head around, but I was wondering what your thoughts were on that.
Can I respond?
Yes.
Okay. So for your first question, if I understand correctly, you're asking potential spillover effect, right? So kind of. Yeah. So actually, in this framework, we don't allow spillover effect. The suitable assumption is still there. That's an implicit assumption. Yeah. And to your second question, the blood pressure example. So remember that the main motivation in this approach is to say we need to link our instrument on the treatment on how we need to link how instrument affects people's treatment taking decision based on social scientific theory. So I think if you don't have good theory on justifying that, and then we probably wouldn't suggest you to do this framework. Yeah.
What I would say is you should think of as the prototypical example for this as an encouragement design.
Yeah.
Where
okay.
we don't have control over whether you get the treatment or not, but rather we can encourage you to take it, just as the government can't force you to listen to its propaganda, but it can encourage you to listen. And we can study things on the encouragement, but then there are people who won't take it up even if you encourage them, and there are people who will take it up despite the fact that they were never encouraged. And those non-compliers have potential treatment effects in a study in which they were forced to take the treatment. And that forced to take the treatment is like interesting for social scientific context where you're thinking about expanding the program beyond the people who are just marginally encouraged. So like in the case of the vaccine, let's suppose that we wanted to figure out the effect of the vaccine, but it wasn't something it was people were signing, it was something people going out and buying in a store. And the government couldn't control, didn't want to invest in a real experiment. So what they did was they said, let's compare the stores that are open more often and less often. That kind of encourages people to go buy this thing. Well, some people are going to get the vaccine even if the store is only open for 5 minutes, and some people will never get the vaccine even if it was open for another 5 minutes. And so those non-compliers are maybe the most vulnerable people in the population that you want to know, or the least vulnerable people in the population that you want to know the effect of this drug is. And so this technology is designed to target those two populations, the people outside the people who are most encouraged by the instrument.
I see.
And it's not so much about the general equilibrium effects that you're describing, which are also very important and something you could get at with a model, but we're not there yet.
Yeah, very interesting. Yeah, no, that's very helpful. And if that's the case, I don't know how far along you are on this paper, but another example that you might want to consider. Just maybe thinking about, or at least thinking about a response to if someone else mentions it, is the kind of Vietnam lottery. I think that sounds like it might be a good example for this particular design, and it makes it clear that you're conceptually what you're interested in is kind of like this subset of problems where there are instruments which encourage behavior. Encourage people to take the treatment, right? Mm. Because I mean, a lotto is technically the Vietnam War lotto is random, but you also, again, the local average treatment effect is also for the compliers. Like you have to not only get the lotto number, you also the right lotto number. You also have to, some people went to jail, they didn't care, right? So you also have to be willing to go be deployed. So so just something to consider. This is very interesting though.
Thank you.
Yeah. Well, thanks for the paper. It's great. Okay, so I guess that then I am the only person left for this panel, and we're a little bit over time, so